Good afternoon to everyone. Now we start the session, and first we welcome to our Professor Datar for continue this session, and welcome to all participants to join this session. So thank you very much, Professor, and continue this session.
Thanks again for the introduction. So today I want to talk about in this last lecture, at least for me, I want to talk about the Koshiriman equations. So I mean, the complex plane, at least as a topological space, is the same as R2, right? So if you're given a map between two sets in the complex plane, you can also interpret that as a map between two open subsets or two subsets of R2, right? The two-dimensional Euclidean space. And then for maps between two-dimensional Euclidean spaces or Euclidean space of arbitrary dimensions, there is already a notion of differentiability that we learn in calculus, right? In multivariable calculus. So it's of course a natural question to ask, how is that differentiability actually related to holomorphicity, right? So that's the question I want to address in today's lecture. So before going on to holomorphic functions and this beautiful characterization in terms of the Koshiriman equations, let me just give you a very brief overview of multivariable calculus, just as a just to sort of remind you of stuff that you might already be very well familiar with. Okay, so the setting is the following. So let omega for now be an open subset of R2. Okay, so and let F, which I'll denote the first component by U and the second component by V, be a map from omega to R2. Okay. So then obviously U and V are both going to be basically real valued functions on omega, and U is going to be a function of two variables, and similarly V is going to be a function of two variables. Okay. So just to draw a picture, you have some open set in R2, let's say. Right, and then you have this map F. So it takes a point xy lying in this domain to a point f of xy, which I'll denote as the pair u of xy comma v of xy. So the first component of f is given by u, the second component of f is given by v. Okay. So then here's a definition that we learn about in a multivariable course. So we say that f is, I'm going to use, because I want to differentiate between sort of complex differentiability and real differentiability. So I'm going to call this real differentiable. Of course, in a calculus class, we basically just call it differentiable, right? So just because I want to distinguish between this differentiability and our complex differentiability, I'm going to call this R differentiability. So we say that f is R differentiable at a point P, whose my notation will be, I'll denote the coordinates of this point P by A comma B. So this is some point in omega. So we say that our function is R differentiable at this point if there exists a linear map okay, from R2 to R2 such that the limit as absolute value of h goes to 0 or the norm of h goes to 0 if you look at f of p plus h minus f of p, divided by this is going to be 0. Okay, so I hope all of you are familiar with linear maps. So what does this term linear map means? So that just means that if you take any two vectors, so let me do it this way. So if you take any two vectors h and k, then a linear combination of this is basically given by dfp of h plus mu times dfp of k. Okay, and then we basically call dfp, this linear map, the derivative or the r derivative of okay. So there's this change of perspective when you learn multivariable calculus. I mean, when you learn one variable calculus, the derivative of any function, any differentiable function, is another function, right? But the change of perspective for multivariable calculus is that derivatives now become linear maps. Okay. All right. So then a remark, or maybe I should just write down a few facts that are well known, that if f is r differentiable at this point p, this implies that f is automatically continuous at p. Right? Exactly like we had in one variable calculus, exactly like we had even for C differentiability. Okay. Now, of course, you know that linear maps, there is a correspondence between linear maps and matrices, right? So this is a linear map from R2 to R2. So there'll be a corresponding 2 by 2 matrix, but this correspondence is only when you choose a particular basis for your vector space, right? So of course, R2 comes with a standard basis. So we denote the standard basis of R2 by E1. So I'm going to denote them as column vectors 1, 0 and E2 as 0, 1. Right. So in the picture, your E1 vector is basically this vector, and your E2 vector is basically this vector, right? So this is E1 and this is E2. So of course that gives you a basis for R2. So any other vector H can be expressed as H1 E1 plus H2 E2. Okay, so then my notation will be, I'll denote the vector H as a column vector with its components H1 and H2. Okay. So then using these, I can actually define the partial derivative. So maybe let me give a definition independently. So we define the first partials of f by, so I'll denote this by del f by del x, but remember f itself is a vector valued function. So what this actually is I mean, this is basically del u by del x and del v by del x. Okay, because u and v were basically the components of f, right? So where did I right? So what is the x partial
Please
derivative
rotate
of
the
f?
screen, sir. Sir,
Yeah.
please rotate the screen, sir. Rotate the screen, sir.
Why screen is very good condition?
Yeah. Why should I?
No, screen is very good condition. No need to rotate.
Because I mean, there's a issue for some students that or some participants that they were not able to read because it was too tiny. If I rotate
Maybe
the screen.
Professor Ved, you can increase the thickness of the pen so that it's maybe dark, little dark.
I see, but
you don't need to rotate it. Yes.
okay. Okay, so the x partial is basically defined at this point, let's say p, by simply you take the derivative and apply it in the E1 direction. So the derivative is a linear map. So you apply it to the E1 direction, you get another vector. The x component of that vector is going to be this. The y component of the vector is going to be the partial of v. Okay, so this is a definition of the first partial. Similarly, you can take the first partial in the direction of y, right? So this is going to be del u by del y and del v by del y. And you define this to be this. Okay. And then you define the Jacobian matrix is actually defined as JF at P. This is equal to, so sometimes I'll also use the notation. So this is a piece of notation. Ux will basically be equal to del u by del x. Uy will be equal to del u by del y. So this is just some convenient notation. Similarly for v, Vx is equal to del v by del x and Vy is equal to del v by del y. Okay. So then the Jacobian matrix at P is basically just defined as Ux of AB times then Uy of AB, then Vx of AB and Vy of AB. Okay, remember that P was basically this point A comma B. Okay.
Sir,
Yeah.
sir, del f upon del y at P is equal to dfp e2 vector y.
Yeah, that's right. Are you asking why or?
Yes, y it is equal to dfp at e2.
Right. So you can take this as a definition, but let's try to understand where this comes from. So recall that what is the definition of partial derivative? So let's do real valued functions, right? So by definition, this is basically just this, right? The limit as h goes to 0. Now h is a real number, such that you take, let's say you're calculating at p, right? So you take this vector p plus h times this vector e1 minus this, right? Do you agree that this is the definition of the first partial derivative? Right?
Yes.
Right. So now let's try to right. So similarly, del v by del x is basically just this. Okay, so let's try to understand what is so similarly, I mean, del f by del x should actually be, I mean, the limit as h goes to 0 of f of, you just do this component wise, right? Okay. But now, just call this a vector, right? So how should I put this, right? So on the other hand, by our differentiability, we know the following, that the limit as h goes to 0 of f of p plus h e1 minus f of p. So just look at the definition of our differentiability, right? This is the definition. Okay, so you have to take f of p plus h, where h is a vector here. So I'm applying this definition to a vector given by h times e1. Okay, so if you apply this definition to a vector given by h times e1, then you basically get this. Right, this is 0. Do you agree?
Yeah, yes, sir. Yes.
But now, I mean, my claim is that del f by del x is basically equal to this, right? So how do you prove this? I mean, you know that, right? So what is del f by del x minus del fp by e1? So by definition, this is the limit as h goes to 0 of f of p plus h e1. Or actually, let me just look at this earlier limit a bit more. So what is this limit? This is the limit as h goes to 0, f of p plus h e1 minus f of p by h, right? Minus, what is this equal to? This is a linear map, so this is equal to h times dfp of e1, right? H is now a real number. So when you divide, I mean, you can write this as basically this, right? So now when you divide by h, you'll be basically left with this. But we already know that the limit of this is del f by del x, so del f by del x has to be equal to this. Okay, does that make sense?
Yeah, yes, sir. Okay.
Yeah, okay. All right, so then the Jacobian is defined by this. So let me make a couple of important remarks which are sort of always made in a multivariable class. Firstly, note that existence of partial derivatives does not imply our differentiability. Okay, so just because partial derivatives exist, that does not mean that your function is differentiable. Okay, so I mean, there are, if you haven't seen this before, I urge you to, I mean, just give a Google search and you will find many counterexamples, right? So maybe if you haven't seen this before, take this as a sort of reading exercise. Another thing to note is that if partials exist and are continuous, then this implies that your function is R differentiable. Okay, so so this is another sort of well-known theorem that's proved generally in a multivariable class. Okay, so now I want to go on to the main topic for today, namely Koshi-Riemann equations. Oh, so maybe I should, sorry, before I go on to this, so maybe I should just answer, say another thing about this R differentiability. So R differentiability implies that f is well approximated by a linear function. Okay, so essentially this notion of R differentiability comes about because you want a good linear approximation to your function. I mean, I can't draw the graph of a sort of I mean, I can't draw the graph of a function from R2 to R2, but if you want to think about a real valued two variable function, then the idea is that if the graph looks like, for instance, a paraboloid, then the idea is that you should be able to approximate the graph by sort of the tangent plane to your parabola at that point. Okay, so this is of course the graph of a linear function, and you'll see in the proof of our main theorem for today, you'll see you'll see this coming up essentially. Okay, so I don't want to write this formula and then again rewrite it during the proof. So just have some patience. You'll see this linear approximation popping up in the proof of our main theorem. Okay. All right. So so let me move on to Cauchy-Riemann equations. That's the main topic for today. Okay, so recall, if you have a function f from an open set in C to C, then this is called C differentiable at a point P if this limit exists, right? So now h is allowed to be a complex number, and we call this limit the complex derivative of f at p. Okay. So now let us write z as x plus iy, or as a pair. I mean, if you think of complex numbers in terms of the Argand plane, then you can think of it as a tuple of real numbers. And let us call f as u plus iv. And again, in terms of the Argand plane, this will basically just be the pair u comma v. Okay. So where u comma v are now real valued functions on this set omega, and you're thinking of this set omega as a part of R2. You're thinking of the complex plane, I mean complex numbers as the Argand plane. Okay. So here's a question that I wish to answer. Okay, what is the relation between C differentiability of f and R differentiability of f? Okay. So this is the first question, and the second question is a slightly weaker question. So if f is C differentiable at this point P, I want to ask, does this imply that the partial derivatives exist? Okay, so as in my earlier remark, just the fact that the partial derivatives exist does not mean that f is R differentiable, right? In general. So at least are the questions clear? Hopefully. Okay, so let's analyze at least one direction. Okay, so let's analyze one direction before I state the main theorem. So suppose f is actually C differentiable at P. Okay, then let's try to understand what happens. So C differentiability by definition means that this limit exists, right? Now the idea is to look at the complex plane and basically allow h to go to 0 along the coordinate axes. Okay, so I'm going to allow h to go to 0 just along the coordinate axes. Okay, so so in the definition of C differentiability, so the case 1 is, suppose h is basically just a real number. Maybe I should use better notation here. So let's say h is basically given by this complex number. Okay. So this means that I'm approaching 0 along the x axis of the Argand plane. Okay, so then what is f prime of P? By definition, I mean, it's just this limit, right? Sorry, I should write it. Maybe let's write it down carefully. So it's, I mean, by definition, it is this. But then h is equal to lambda, which is now a real number. So this is the same as lambda going to 0 of u of x plus lambda comma y plus, okay, I need more space, sorry. So this is the same as the limit as lambda goes to 0, u of x plus, sorry, a plus lambda comma b minus u of a comma b. So remember, my p is always equal to ab, right? That's the notation I'm sticking with. Divided by h, so that's the real part of this difference quotient, plus I times the limit as lambda goes to 0 of v of a plus lambda b minus v of ab divided by lambda. But now you notice that, I mean, what is this limit? You have a real valued function of two variables and you're only varying the first variable and taking the difference quotient, right? So by definition, this will just be del u by del x at the point a comma b plus I times del v by del x at the point a comma b. Okay, so this implies that del u by del x and del v by del x firstly exist at this point a comma b, and we basically have these equalities. We have that this is equal to the real part of f prime of p, and this is equal to the imaginary part of f prime of p. Okay, so just from assuming holomorphicity, we have this conclusion. Now let's do the second case where h is now equal to I times nu. So it's a purely imaginary number. Okay, so it's purely imaginary, where mu is some real number. Okay, so this corresponds to approaching 0 along the y-axis. So now let's calculate this limit again. Okay, so again, what do we get when we do f prime of p? That is limit as h goes to 0 of this. But now h is I times mu. So that's the same as the limit as mu goes to 0. U of a comma b plus mu minus u of a comma b divided by h is I times mu. So you will have a I times mu in the denominator. And then plus the imaginary part, which is given by this. Sorry. Okay, so the I here cancels. And this I, if you take it to the numerator, you will get a minus I, right? So you can rewrite this as limit mu goes to 0 minus I u of a b plus mu minus u of a b divided by mu, plus the I disappears now, and you get this. So once again, this is basically just going to be the partial of u in the y direction, and this is going to be the partial of v in the y direction. So this is going to be precisely del v by del y minus I times del u by del x. Sorry, del u by del y. Okay, so the conclusion is that del u by del y and del v by del y exist, and in fact we have that this guy is actually equal to minus the imaginary part of f prime of p, and this guy is actually equal to the real part of f prime of p. Okay, so we have basically calculated the same limit but in two different ways. So of course the limit is unique, so both the answers should be the same, right? So by the uniqueness of limit, so we equate the real part. So the first calculation showed us that the real part of this derivative was del u by del x, and here we get del v by del y. So we basically get that del u by del x should be equal to del v by del y. And if you equate the imaginary parts, you basically get that del u by del y, which is minus the imaginary part. So maybe I should write it like this: del v by del x is minus del u by del y. Okay, so just assuming holomorphicity, we basically prove that not only do the partials exist, but they actually satisfy this system of partial differential equations at that point, right? So these are basically called the Koshi-Riemann equations. Okay, so I'll usually denote them by CR. Okay, so assuming holomorphicity, you get that the CR equations are satisfied. What about the converse? So suppose the CR equations are satisfied, does that imply holomorphicity? So here's an example. So consider the function f of z to basically be mod z squared, right? And let P be any non-zero point, okay? So in terms of the real coordinates, this is basically just x squared, y squared. Okay, so that means u of xy is basically just x squared, v of xy is basically just y squared. Okay. And now let's calculate the partial derivative. So let's compute the Jacobian matrix. So
u of comma y
Sir,
is
V
x
is 0.
plus y squared.
oh yeah, v is 0. Sorry. Yeah, thanks. V is 0. So this is and v is 0. Yeah, thanks. Okay, so let's compute the right. So I mean, this right away tells you that del v by del x and del v by del y are both 0. Okay, but then oh, actually, this is not a good example. I wanted an example of okay. Let me make my point, and I actually wanted right. Okay, let me complete this example and then I'll make my point. So here clearly if P is not equal to 0, then CR equations cannot be satisfied. Right, because what is del u by del x? Del u by del x is 2x, del u by del y is 2y. Right, and by Koshiriman equations, these two have to be equal to 0. But that, I mean, if P is not equal to 0, at least one of them is not going to be equal to 0. So Koshiriman equations cannot be satisfied, which means that that mod z squared is not complex differentiable away from the origin. Okay. So just by our calculation, because if something is complex differentiable, you have to automatically satisfy CR equations. So another example is something like this. Right, so right, so what? Let me just look up this is actually an assignment problem, a tutorial problem. So let me just make sure that I have the function correct. Right. So if you look at this function, then this actually satisfies the Koshi-Riemann equations. At the origin.
Point at 0 point. Yes. But not if
yeah, so, sorry, did you have a question or?
Or please mute your mic, Sandeep Kaur.
So f satisfies the Koshi-Riemann equations at the origin, but f is not C differentiable at the origin. Okay, so I'm not going to work this out. This is a tutorial problem. But what this means is that what this means is that the converse is actually not true. If you just satisfy the Koshi-Riemann equations, that does not automatically imply C differentiability. Okay, so So what is the correct converse? So here's the main theorem for today.
Sir,
Yeah.
sir, is there any relation between Koshi-Riemann equation and that that Jacobian matrix which you described earlier?
Yeah.
Jacobian
So this is basically equivalent to the what is the Jacobian matrix? So the Jacobian matrix is basically just ux, uy, vx, vy, right? So the Koshiriman equations will basically imply that the Jacobian matrix is ux, uy, and then you replace vx by minus uy and ux, right? So in other words, it's a skew. The diagonal terms are basically the same, and the off diagonal terms are negative of each other, right? So that is equivalent to the Cauchy-Riemann equations being satisfied.
So its determinant is mod fz square.
Right, exactly. That's also a good point. So so note that. So maybe let me make a remark that the determinant, and in fact this is actually quite useful in the subject that I work in. Exactly, the determinant of the Jacobian matrix will actually be f prime mod square. And in fact, there is a tutorial problem, I think, also on this. So for instance, I mean, you have the inverse function theorem in which you learn in calculus. Then, I mean, using this observation that the determinant is actually mod f prime squared, you can actually prove a holomorphic version of the inverse function theorem. Okay, so this is an important observation. Okay, any other questions? Okay, so let me write down the main theorem. So let's say I have an open subset of C, and let's say I have a function which I denote by u plus iv. So this is a function from omega to C. Then the following are equivalent. Okay, so the first point is that f is C differentiable at a point P in omega. Okay, and the second condition is that that f is R differentiable at the point A comma B. So now I'm thinking of this point P as A comma B, and U and V satisfy the Cauchy-Riemann equations. Okay, so just the Cauchy-Riemann equations do not imply complex differentiability, but Cauchy-Riemann equations and R differentiability does imply C differentiability. Okay, so I hope the statement of the theorem is clear. Okay, so how do you prove this? So proof is actually not very difficult. So whenever you have a set of equivalent conditions, you need to basically prove a forward implication and a reverse implication. So let's first prove the forward implication. So suppose f is C differentiable at this point P. Then by the above discussion, right, so by the above discussion, del f by del x and del f by del y exist. So all the first partials exist, and u and v satisfy the Cauchy-Riemann equations. right? That we just saw a few minutes back. So to complete the proof, I need to prove the following claim, that f is also R differentiable. Okay, so, and in fact, so if you take the linear map, which is the derivative map, this is precisely given by f prime of p times h. Okay, so here I'm basically, I mean, this is a vector in R2, and this is a complex number in C. So I'm basically identifying vectors in R2 with complex numbers, I mean, with the complex plane. Okay, so that's how you should understand this equality. Okay, so let's prove this. Okay, so we let right, so how should I write this? So we take this as a definition. The definition is basically just that this is the Jacobian matrix acting on okay, so I'm defining this map DFP, and then I want to show that this DFP map actually happens to be the R derivative. That's my aim. Okay. So by the Koshi-Riemann equations, this is, as somebody pointed out, that the Jacobian can be rewritten using the Koshi-Riemann equations. So let's do that. So that's just minus uy and ux. Okay. So if you do this calculation out, that's just going to be ux times lambda plus uy times mu, and then minus uy times lambda plus ux times mu. Okay, I hope this is okay. I mean, this is just matrix multiplication. But now recall, what was the derivative? So let's go back to our calculation. So the derivative had real part del u by del x, imaginary part del v by del x. So this was precisely del u by del x, or in my notation, this is precisely ux plus I vx. But what is vx? Again, by Koshi-Riemann equations, what is vx? That's just minus uy. Okay. So the derivative was basically just this from the Koshi-Riemann equations, right? So let's calculate the following. So let's compute f prime times this complex number lambda plus I mu. Okay. So that's going to be ux minus I uy times lambda plus I mu. Okay, so let's do this calculation out. This is ux lambda. You have a minus I uy times this, so plus uy mu, and then plus I times minus lambda uy plus mu ux. Okay, but those are exactly the components here. So if you look at the first component, that's precisely this. And if you look at the second component, that's precisely this. Okay. So what that tells you is that this acting on lambda mu is precisely f prime times lambda plus I mu. Okay. So I think of this as my vector h, and this as my complex number h. Okay. All right. So now, how do you prove differentiability? What do you have to check? So to prove differentiability, we need to calculate limit as this vector goes to 0 of the following. F of p plus h minus f of p minus df at h divided by so this, right? But if you think of h as your vector lambda mu, then by the above calculation, this is the same as the limit as this complex number goes to 0 of f of p plus h minus f of p minus what is dfp at h we have just calculated. This is precisely f prime of p times the complex number h, right? And then you're taking the modulus of this. But this is precisely 0 since f is complex differentiable. Okay, so complex differentiability implies that this limit is 0. So we have shown that our original limit is 0, which implies that f is R differentiable. Okay, any questions? Yeah.
Any C-linear map is R-linear.
Sorry, can you repeat?
Yes, any C-linear map is R-linear.
Any C-linear map is R-linear,
Yes,
but the
from that-
converse might not be true, right?
Yes, from that we can conclude this part, right?
Right, but no, sorry, I don't quite understand.
No, I am saying this DFP will
Right.
act as a R-linear map also.
That's right.
So we can find a candidate for R-linear map, and that the limit.
Yeah. So the point is that you're right. So this, I mean, I'm saying that this df p is actually sort of multiplication by f prime of p, right?
Yes.
And f prime of p is C linear. I mean, multiplication by f prime of p. In particular, it will also be R linear. Yeah. So that in particular, I mean, sure. So you can also do it this way, but I mean, you have to still use the Koshiriman equation somewhere, right?
Yes.
Yeah. Okay. So that's fine. Now let's do the converse. Okay, so for the converse, we are assuming that f is R differentiable at this point P, and U and V satisfy Cauchy-Riemann equations. Okay, so let's try to understand what. So this is where the sort of linear approximation comes in. So recall that our point P is basically A plus IB, and we are going to take two quantities. So I'm going to define this capital A as del u by del x at AB, but by the Cauchy-Riemann equations, this is also equal to del v by del y at AB. Okay, so I'm going to call that number capital A. Similarly, I'm going to call this number capital B, which is sort of del v by del x at A comma B. But again, by Cauchy-Riemann equations, this is the same as del u by del y with a negative sign. Okay, but we have an additional assumption. We also know that f is R differentiable. So what does that mean? So f is R differentiable at P implies we have the following set of equations, which I'll call as star. So this is the linear approximation. So that means that if you take u evaluated at a plus h and b plus k, then this is going to be u evaluated at a plus b plus h times ux at a b plus k times uy at ab plus epsilon 1 of hk. Okay, and similarly, so this you should think of as some error term. I'll specify what is the special property of this error term. Similarly, you can write an expansion for v. So you can write this as v of a plus b plus h times v of x ab plus k times v of y ab plus epsilon 2 hk, where I'm sorry, I should stay consistent with my notation. So let me stay consistent with my earlier notation. I was using lambdas and mu's. So this is lambda times this plus mu times this. And this is again lambda mu. This is lambda mu, lambda mu. Okay, where the limit as lambda mu goes to 0, 0 of epsilon 1 of lambda mu divided by the square root of lambda squared plus mu squared. So this is basically the absolute value of the complex number lambda plus I mu. This is supposed to be 0. Okay, and similarly for the second error term. Okay, so when you say linear approximation, you actually mean that this u can be approximated by a linear function up to an error, right? And that error has to basically decay to 0 faster than any linear function. That is what linear approximation basically means. And that is what you get from differentiability. In fact, that is equivalent to saying that f is R differentiable. Okay, so this is basically the linear approximation. Okay. So let me rewrite this in terms of these numbers a and b. So this system is basically equivalent to the following system. So u of a plus h, a plus lambda, b plus mu is basically u of ab plus lambda times a minus mu times b plus this error term. And similarly, you have an expansion for v. So this is going to be lambda times b now and plus mu times a. Okay, so I'm going to call this double star. So remember, I have to prove complex differentiability. Okay, so what is my goal? So my goal is that the limit as lambda plus I mu goes to 0 of f of lambda plus, sorry, f of p plus lambda plus I mu minus f of p divided by lambda plus I mu. My goal is that this converges to a plus ib. Okay, so this limit exists, and that means that f is going to be c differentiable, and the c derivative is going to be given by a plus ib. Okay, so that's the goal. So let's try to analyze what this difference quotient is. So what is this? Okay, so if you write this down carefully and using basically star. So I don't want to do all the calculations, but I urge you to go back and do all these calculations by yourselves. This will turn out to be the following. So I should do this carefully. Right. So this is basically just going to be lambda of a plus ib minus mu of b minus ia divided by lambda plus I mu, plus you have the error terms. Okay, with an I here. Okay, so let's call this term as I1 and this term as I2. So then by the fact that these error terms basically satisfy this, you can actually show that the limit as lambda plus I mu goes to 0 of I2 is actually going to be 0. Okay, so I'll leave this as an exercise. So check that I1 is actually, I mean, you can sort of multiply and divide by the complex conjugate. This is basically just going to be a plus ib. Okay, so in other words, when you let lambda plus I mu go to 0, this entire thing is basically just going to converge to a plus ib. So since I'm running a bit short of time, I don't want to do all these calculations, but I mean, it's a good exercise to check these two things. Okay, so basically, if you assume R differentiability and Koshiriman equations, then you get complex differentiability for phi. So this completes the proof of the theorem. Okay, so we have proved that 2 also implies 1. So let me maybe make a remark. So the proof actually shows that f prime in terms of the real and complex parts is basically given by this. And it's also equal to, I mean, ux is equal to vy plus I times vx. Okay, so these are very important formulae also. The complex derivative in terms of the partials of the real and imaginary parts. Okay. All right, so maybe let's pause. Are there any questions at this point? Because next I'm going to talk about some consequences of this theorem.
So R differentiable is same as Fresher differential.
Yeah, I mean, in this case, yeah.
And is there any other
Shear
differentiation
differentiability generally is used for more
function analysis?
for Banach spaces and so on. So, I mean, this is much more basic than that, right?
Okay.
Yeah. Okay. Any other questions? Okay. If not, let's go on to some consequences. Okay, so I have two consequences, and then if time permits, maybe I'll also talk a bit about harmonic functions, but that's only if time permits. So the first consequence is something that we used last time, but and I promised you that I'll give a proof after we discuss Koshiriman equations. So the first corollary is the following. So let omega be connected. And f be holomorphic on omega. Okay. So suppose f prime of z is equal to 0 for all z in omega, then f is identically equal to a constant. Okay, so how do you prove this? So f prime of z equal to 0 implies that ux minus I uy equal to 0, because remember this very important formula of the complex derivative in terms of these partials, and it also implies that vy plus I vx is also equal to 0 on all of omega. Right, but then that implies that all the partials are 0. So then we can just apply the mean value theorem from one variable calculus, right? So suppose this is your omega. We know that the derivative of u in the x direction is always 0. So it has to be constant along the x direction. Similarly, the derivative along the y direction has to be constant. I mean, is 0. So u also has to be constant along the y direction. So the mean value theorem from one variable calculus, so which we almost, I think, also study in high school. This implies that u is a constant and v is a constant. But then that implies that f is a constant. Okay, so right, so that proves, I mean, if you remember, we had used this this fact in basically proving that the exponential function is the unique function which satisfies that particular differential equation, right? Okay, the second corollary is actually much more interesting. So this, again, this is something I had stated as a fact at the end of yesterday's lecture, and I had said that you need to introduce Koshi line integral and so on to prove this. But at least one part of it I can actually prove using just line integrals that we learn in a multivariable class, I mean multivariable calculus class, right? So I thought maybe I'll just prove that for you. So let omega be an open set.
Sir.
Yeah.
Sir, in first corollary, where is the connectedness of domain is used?
Oh, that's because of, I mean, this implication, right? So this uses connectedness. Because the point is that, let's say you are at some fixed point z0, right? Now, suppose your set is connected, then you can connect Z0 to Z by some line, by some path, right? And then the idea is you basically just, I mean, if you know that the gradient of U is 0, by the fundamental theorem, the values of U at these 2 points will be the same, right? But that's no longer true if you can't go from Z0 to Z by a path. Okay, does that make sense?
And also we can reach this Z0 to Z using lines parallel to x-axis and y-axis. And lines parallel to x-axis it's constant, lines parallel to y-axis it's constant.
Right, but wait, is that true unless you have some convexity or something?
No, connectedness is required here. Path connected we are using.
Path connected, sir.
Yeah, but path connected, can you always join by horizontal and vertical
Yes.
lines?
That means initially we proved that lines parallel to x-axis is constant. Lines parallel.
No, I understand that, but I mean, I'm just thinking that suppose you have a, let's see. So I guess I guess you're right. So what one can do, I mean, if one has a complicated domain like this, one can always draw small, I mean, go in some polygonal path, right? Is that right? Right? Because just using two lines you might not be able to reach, but yeah, you can always do it using some polygonal path. Right?
Yes.
Yes, that's right. So yeah, that's probably a simpler way to see
because
this.
if we remove the connectedness, the f dash of z can be 0, but f need not be constant.
Yeah, of course. So if you have, I mean, if it's if omega consists of two connected components, you can very well have that f is identically 1 here, f is identically 0 here, right? And the derivative is 0, but f is not constant. Okay, so connectedness is used in this step. Okay, does that answer your question?
Yes, sir. Yes.
Yeah.
Okay.
Okay. All right. So moving on to the next corollary. Suppose you take an open subset of C containing the origin. Okay. Then my claim is that there does not exist a function f which is holomorphic on omega such that the exponential of f of z is equal to z for all z. Okay, or equivalently, I'm saying that there exists no holomorphic logarithm on this domain omega. As soon as it contains, sorry, I should, it doesn't contain the origin. Of course, you can't define the logarithm at the origin. So I should say be an open set C containing this small disk. Okay, so let me draw a picture. What I mean is that suppose you have some open set. Of course, that does not contain 0, but it contains this disk closure minus the origin. Okay, as soon as it's a domain that contains this set, there cannot be a holomorphic logarithm on it. So is the statement clear? Any questions on the statement?
Sir, repeat the statements.
Okay, so maybe let me rewrite it. Sorry, maybe let me rewrite it in with more clarity. So let omega be an open subset of C with the following two properties. So the first property is I don't want the origin in omega. because I want to define a logarithm. The second property is that there exists a delta positive such that if you don't even need the full disk. If you look at the boundary of this disk, that is contained inside omega. Okay. Then there does not exist a function, a holomorphic function on omega, such that the exponential of f of z is equal to z for all z. Okay. So in particular, there is no, so maybe I'll include that as a remark. So remark, in particular, the following sets have no holomorphic logarithm. Okay, so for instance, you can take C star. I mean, ideally, in an ideal world, you would like to define a holomorphic logarithm in all of C star. But C star satisfies these two properties, right? So if you look at C star, then of course you can, I mean, for any radius delta, if you look at the corresponding circle, that is of course going to be contained in C star. So it satisfies both these conditions. So there cannot be a holomorphic logarithm on it by this theorem. Secondly, you can also look at annuli, right? So you can look at annuli which are defined as a set of complex numbers such that the absolute value is between R and R. Okay, so these are sets of this form. So again, this cannot have a holomorphic logarithm on it. Okay, so as soon as you can go sort of around the origin, as soon as you have a curve that goes around the origin, you cannot have a holomorphic logarithm. Okay, and so let me prove this this theorem. So I hope the statement is now clear, right?
Sir?
Yeah.
Sir, I think that any curve around the origin cuts the negative real axis, and that is the reason why logarithm does not exist.
Yeah, but how do you prove that? So you have already constructed some examples of logarithm where you sort of have this branch cut, right? But how do you prove that it's important? I mean, so the problem with constructions is that perhaps we are just not being clever enough, right? Perhaps if we are much cleverer, we might be able to come up with some logarithm that even though this cuts the negative x-axis as you point out, perhaps it's still possible to construct a holomorphic logarithm. So you need a proof that this is impossible, right?
Okay.
So right, so this is a proof of that something is impossible. No matter how clever you are, you just cannot do it because it's impossible. I mean, I'll give you a proof. Okay. Right. So I hope the statement is now completely clear. So let's prove it. And then I can perhaps stop. So suppose there exists a delta such that this circle is contained inside omega. So I'm assuming condition 2. And suppose there exists a holomorphic function which is a holomorphic logarithm. Okay, so that means we are proceeding by contradiction. So I'm assuming the conclusion, I'm assuming that you have a holomorphic logarithm and I want to get to some absurdity, some contradiction, right? So recall that because the exponential of f of z is equal to z, this implies by chain rule, we did this calculation last class, this implies that f prime of z is equal to 1 by z for all z. Okay? So what is 1 by z? You can, that's just x plus iy. If you multiply by the complex conjugate, you basically end up with x by x squared plus y squared minus I times y by x squared plus y squared. Okay, but suppose f is equal to u plus iv, then what is our favorite formula for the derivative, the complex derivative of f in terms of, say, the partials of v? F prime is basically vy plus I vx. Okay, so this implies that just by comparing the real and imaginary parts, so you compare the real and imaginary parts, this implies that vx is minus y by x squared plus y squared and vy is x by x squared plus y squared, right? So I'm going to call this P and I'm going to call this Q. Okay. So next, I'm going to consider the vector field F given by PQ. Okay. So let's draw a picture. Okay, so the key point is that this is actually well defined and smooth on all of omega, right? Why? Because the only problem point might be at the origin, but we are already assuming that the origin does not belong to omega. Okay, since 0 does not belong to omega. Okay, on the other hand, you basically have this little disk here. Or rather this little circle, which is the boundary of the disk of radius delta around 0. Okay, and of course 0 is not contained in your domain. So now I have a vector field. What I'm going to do is basically just integrate this vector field, calculate the line integral of this vector field, the line integral from our multivariable calculus or from physics. Essentially, think of this f as the force field, and then I'm going to compute the work done as you traverse along this this circle. Okay. So what this tells you is that this vector field f is actually the gradient of this function v, right? Because the x derivative is equal to the x component of f and y derivative is equal to the y component of f. So f is basically just the gradient of v. So if I compute the sort of line integral, going around this circle, this is the same as the line integral of the gradient of v And what do you know about line integrals of gradients along closed paths? So do you remember your, it's basically in physics you learn that if you have a conservative vector field, which just means that a vector field that's the gradient of something, if you go along a closed loop, that should integrate out to 0. The work done of a conservative vector field is 0. So this is 0. And this is basically just the fundamental theorem of calculus in disguise. Okay, but on the other hand, we have a concrete formula for f. So let's calculate this line integral by hand. So on the other hand, what is the line integral of this vector field? So you are going to basically use, you have to parameterize the curve. So you are going to use polar coordinates. So we let x be delta cosine theta, y be delta sine theta. Then what is dx? Dx is minus delta sine theta d theta. And dy is delta cos theta d theta. Okay, and then by the definition of line integral, this is basically just this integral. It's p times dx plus q times dy. But now you have calculated dx and dy. So that is the integral from 0 to 2 pi, because theta goes from 0 to 2 pi. What is p? P is basically given by this, right? So this is equal to p. So you plug in y equal to delta sine theta. What is x squared plus y squared? That is just delta squared, right? So so we also have that x squared plus y squared is basically delta squared. Okay. So if you just plug that in, you're basically going to get minus delta sine theta by delta squared times dx. What is dx? It's minus delta sine theta. I'll put the d theta outside. And then the next term is x divided by delta squared. So what is x? That's delta cos theta by delta squared times dy, which is delta cos theta. And then everything times d theta. So now, of course, there are lots of calculations, and you'll see that this cancels out. So this is basically just sine squared theta plus cosine squared theta d theta. And of course, by our favorite trick identity, this is the integral of d theta, which is 2 pi, which is not equal to 0. So we calculated this integral in two ways. One, using the fundamental theorem of calculus, we got the answer 0. One, using an explicit calculation, we got the answer is 2 pi. So that's a contradiction. So that completes the proof of this theorem. Okay, any questions?
Sir,
Yeah.
Sir, suppose we have a curve which does not go through that negative real axis, then on that curve we have a logarithmic branch on that curve.
So you can't say whether on that curve you have a logarithm, because you want to define a holomorphic function, you have to have an open set, right? So I suppose you're asking what happens if you sort of take a curve that does not pass through 0, right? So something
Yes.
like this. Right?
Yes, sir. Yes, sir.
And in fact, it might also, be much more sort of complicated, since it might even cross the, right. So if it's a curve of this sort, even then you will actually have, let's say your open set is basically some neighborhood of this curve, right? Which does not cross 0, which does not contain 0 in the interior. Then there will actually be a holomorphic logarithm inside this. Okay, so the actual statement is the following. So this is the big theorem which possibly might go back to Riemann. I don't know, but the theorem basically says that let omega be an open subset such that 0 does not right. So how do I want to say this? Right. So 0 does not belong to omega. And the key point here is that omega is simply connected. Okay, then there exists a f in this such that exponential of f of z is equal to z for all z. Right, so this simple connectedness, basically, I mean, just geometrically, what it means is the following. So suppose you have an open set. What simple connected means is that no matter what complicated loop you take, you can always continuously shrink that loop while all the time staying inside omega. Okay. So no matter how complicated loop, I mean, whatever complicated loop you pick, you can always shrink it down to a point continuously without introducing a tear, as long as you stick to your domain omega, right? Then this, I mean, such domains are called as simply connected domains. So for instance, this is simply connected. On the other hand, if you take the annulus, so let's take the annulus around the origin. Then this is no longer a simply connected set, right? Because if you take a curve that passes around the origin, there's no way to shrink that down to a point without actually going outside the annulus. So in this case, that is why it doesn't have a logarithm. Okay, does that answer your question, or?
Yes, sir. Okay.
Yeah. All right. Any other questions? Or?
Sir?
Yeah.
Suppose we take complex origin. Hello, sir?
Yeah. Your voice
Sir?
was a bit, yeah.
No, sir. Suppose considered a disk with the radius 1, center -2.
Okay.
Then it is also simply connected.
Right. So let's say this is -2 and you want to consider a disk of radius 1, right? Something like this, yeah?
Okay, sir. In this region, we have exponential of f of x is equal to x. There exists a logarithmic function, sir.
Yeah. Yeah, there exists a logarithm here. Yes. So there is nothing special about this the negative x-axis, right? I mean, for instance, C minus any ray is actually a simply connected domain. Any ray emanating from the origin there will actually be a logarithm on this set. Okay.
Sir, in this domain, sir, on this center with -2 and radius 1, if you consider the principal logarithm, principal branch, then sir, the function is not continuous. Then how it can be holomorphic?
No. So that's what. So you don't consider the principal branch. Okay. So because the principal branch, by definition, you have to have the branch cut where you remove the negative x-axis. That's the definition of the principal branch, right? So instead, for instance, I mean, you can do the following. Just remove this, okay? And take the argument to belong to 0 to 2 pi. So the convention is that the argument function is from minus pi to pi, but you can always translate that to say that the argument function is between 0 to 2 pi, right? And then just define, just define log z to basically be equal to log r plus I theta, where z is equal to r e to the I theta, where now theta is forced to lie between 0 and 2 pi. Okay, so that will give you a logarithm that's actually defined on all of this, right? Including this small little disk. Okay, an alternate way of defining it is, of course, using power series expansion. So you can try to define a power series which using successive differentiation. So that's another way of defining the logarithm there. Okay, does that answer your question?
Yes, sir.
Yeah. Okay, any other questions or?
Sir.
Yeah.
So what is that theorem? Which one is that theorem which proves that holomorphic function are analytic function?
Oh, that is, I don't think it has a name, but so that basically, holomorphicity implies analyticity. This actually follows. So this is a consequence of. This is a consequence of the Koshi integral formula. Okay, so hopefully in the next set of 4 lectures, you'll learn about the Koshi integral formula. Okay. All right. Any other questions or?
So if there are no questions, let us thank.
Sir, can I ask?
Yeah, please.
Oh, I'm sorry.
Yeah, you can ask the question if you have.
Yeah, Professor Ved, if it's not too much to ask, I think yesterday you were talking about that proof of Hardy. Which,
yeah. It's not a proof of Hardy. It's a proof in Hardy's pure mathematics. But I think I'm really out of time. So it's there in the typed up notes because it would take another 15 minutes, and I don't know if others are so interested in it. No, that's fine. But so it's actually there in the typed up notes that I had shared with Suman. So you can look at the
share that notes to participants.
Yeah, sure. I'll look it up.
Right.
Thank you so much.
Yeah.
Note is already shared, sir. I have sent the 3 emails.
Sir.
Yeah.
Yesterday, sir. So you are talking about the difference between holomorphism and analyticity. Sir, right. I did not got that point, sir. Can you explain it again, sir?
Yeah. So as of now, so here's what we have proved. Okay. So what we have proved is that if you have an analytic function, so what is an analytic function? An analytic function is any function. Analytic function just means that if you have an open set, given any point z0, there is a Taylor. It has a Taylor expansion in some neighborhood of z0. That is the definition of analyticity, right? But then we proved yesterday or day before, or on Sunday, that all analytic functions are automatically holomorphic functions. Holomorphic basically means that it's complex differentiable. That means this limit of the difference quotients exists, right? So that's the difference between analyticity and holomorphicity. So at least is the difference between the definitions clear?
Yes, sir.
Yeah. So what we showed on Sunday was that analytic implies holomorphic. Next set of lectures, I'm hoping will imply the reverse direction, that holomorphic actually implies analytic. Okay, so that's something to look forward to for the next 4 lectures. Okay. All right.
So are there any questions?
They are same, sir.
Yeah, in the end they are the same. In the end they are the same, but you still haven't proved. I mean, at least, I mean, you might have seen the proof earlier, but we haven't yet proved that, right? But yeah, in the end they're both the same. But again, this is the chief difference between real category and complex category. There are real analytic functions that are always, of course, real analytic functions are also always real differentiable, but the converse is not true. So in the real category, the converse is not true. So this is something really special about the complex category, right?
Yeah, that's what e power minus 1 by x square x naught
exactly.
0.
Yeah.
Are there any questions?
Hello.
Yeah.
Sir. Sir, we have that formula, argument of Z1 into Z2 equal to argument of Z1 plus argument of Z2. Sir, but argument is a multivalued function. Sir.
Yeah, yeah.
How can we make sense of that formula?
Yeah, so of course that formula is completely wrong. Also because of, I mean, you can sort of think of this, right? If you have something with large argument and another complex number with large argument, if you multiply them, so let me just give you an example. Let's say you have the complex number e to the 2 pi I by 3. Right, and then maybe you have something like e to the sorry, what is this? This is pi and pi by 2, right? So maybe wait, what do I want? So I want this to be, let's say, 3 pi by 4. And then I want this to be 5 pi by 4, right? Then if you multiply these two together, the resulting complex number will be whatever, I mean, 8 pi I by 4, so 2 pi I, which is actually, I mean, which is just the number 1, right? So did I do this correctly? Yeah, right. Right. So in other words, the sum of the arguments is actually equal to 2 pi, but the argument of Z1, Z2 is actually 0. So of course, this is not true. So yeah, these sort of simplistic formulae that we study in high school are not quite correct. You have to be a bit careful when you deal with arguments, right? Yeah, Rohit, does that answer your question? Or?
Yes, sir. Sir,
yeah.
Actually, if we make some equivalence relations, then it will make some sense. No?
Yeah, so then it perhaps, yeah, so, right. So if you, that's actually right. So maybe that's a good point. So what do you mean by an equivalence relation? So the point is, if you take the interval, let's say 0 to 2 pi, you want to make the equivalence relation by basically identifying these two, right? So you want to say that 0 is equivalent to 2 pi. But then that is the same thing as basically the unit circle, right? And then the unit circle is actually a group, right? So in that you do have a multiplication that takes you again back to the unit circle. Okay, yeah. So if you make the equivalence relation, then it's actually correct. Yeah.
Thanks.
Yep.
So are there any questions? So if there are no questions, let us thank Professor Datar for a very interesting talk. And he has given in a different perspective. I hope audience enjoyed a lot. And I think most of the things we cannot find out in a routine textbooks. And he has collected nice material and has given into the typed version. So thank you, Professor Datar. We really enjoyed your lectures.
Yeah, thanks a lot for the opportunity. I think I hope the participants were not sick of me by the end of the 4 lectures. So I hope everyone had a good time. And yeah, it was, I think, yeah, such efforts even on the part of the organizers are really nice and probably very important.
Thank you, Professor Ved. And you made this ATM school very exciting to the participants. And I learned now, see, these kind of things are not there in the standard textbooks, like normal textbooks.
Right.
So they got a very nice flavor of the complex analysis.
Yeah, thank you.
Thank you very much.
All right.
So
yeah.
on behalf of all the participants and on behalf of the organizing team, I thank you very much.
Yeah, thanks a lot once again. It was a great experience for me.
Sir, one last question.
Yeah.
So this argument formula Z1, Z2 equals to this one. So on any domain, it can be true. Like if we consider open 0 or close to pi in that domain.
Yeah, any interval of length 2 pi would be fine.
One side opens, right, sir? Yeah.
Yeah, one side open, but yeah, one side open. Yeah. Or you can, a better way to think of this is that you identify the 2 endpoints and think of it as a unit circle.
Okay, sir.
That's another way to think of it. Yeah.
Okay, sir.
Okay. Yeah, I guess I'll sign off. Thanks once again to the organizers for the opportunity.
Thank you so much.